All right, so this is the last video from the 3.5 notes, and this one is going to cover the rational root theorem. We'll define it here and then do a couple of examples, and then you can go do your 3.5 practice. All right, so if a polynomial p of x has integer coefficients, do you recall what integers are? They are all the whole numbers and their opposites, so we're not talking about decimals or fractions or anything like that. I mean, any integer can be written as a fraction by putting it over 1, but I'm just talking about -3, -2, -1, 0, 1, 2, 3, and they continue both directions towards negative infinity and infinity. So when you're reading a definition in math, make sure that you understand every term inside of the definition or in the theorem. So a polynomial p of x has integer coefficients, then every rational root. Rational numbers are numbers that can be written as fractions versus irrational numbers like irrational numbers are the numbers like pi that go on forever, never end, and never repeat, or perhaps like the square root of 2, or numbers that involve I, the complex. You could have complex roots. So we're talking about just rational roots, roots that can be written as fractions. I'm going to start over. If the polynomial p of x has integer coefficients, then every rational root of the polynomial equation p of x equals 0, so we're finding zeros, can be written in this form: p divided by q, where p is a factor of the constant term of p of x, and q is a factor of the lead coefficient of p of x. Oops, this did not get erased here. All right, so we are going to do this example right here. We're going to find all possible rational roots of this polynomial for part A, x cubed plus x squared minus 4x minus 4, and then we're going to factor it completely. So our possible rational roots are going to be of the form p divided by q. P is the constant term, so p is equal to -4. So we're going to list the factors of p. Again, p comes from the constant term, which is the term, if it's in descending order, it'll be the last term, and it will be a term that has no variable. Hence the name constant, because it doesn't vary. Factors of p include plus or minus 1, plus or minus 2, plus or minus 4. Then the, so that's from this number right here. And then we have q is a factor of the lead coefficient, and our lead coefficient here is 1. So q equals 1 for this polynomial, and the factors of 1, or factors of q, are just plus or minus 1. So what we need to do now is we need to find all of the combinations of factors of p divided by factors of q. So if I take positive 1 from, we have two, that's really two factors, positive 1 and negative 1. If I take positive 1 and put it over, so I'm taking all of these numbers that are in red, dividing by the numbers in green. So 1 divided by a positive 1 is 1. I could do 1 divided by a negative 1, that's going to be -1. I could do -1, because I have a -1 up here, divided by a positive 1. Or a -1 divided by a -1. But now pay attention to this, because you are going to be able to take a shortcut. Anytime you have a combination of plus or minus 1 over plus or minus 1, you're going to end up, this is 1, this is -1, this is -1 again, which repeats, and this is positive 1. We don't need to list those. So basically when you do plus or minus 1 over plus or minus 1, the result is you're going to have either positive 1 or a -1. So plus or minus 1. So possible rational roots or rational zeros is what we're trying to find. 1 could be, -1 might be, and then we got to go to this next set of factors. Plus or minus 2 over 1 is just plus or minus 2, and then we have plus or minus 4. So if this lead coefficient had been something other than 1, we'd have more than just the factors that show up on the top. We'd have to divide by, well, yeah, I'll show you in the next example. Okay, so let's see here. We have these possible rational zeros, and so what we want to do now and you may need to get a piece of scrap paper to do this, but we're going to factor this completely, and what we're going to do is we're going to check to see, using synthetic division, which of these is a factor of this polynomial right here. Positive 1, negative 1, positive 2, negative 2, positive 4, negative 4. And we have to go through all of them and check until we find one that works. All right, so I'm going to start with 1. I'm using synthetic division, and you just use the possible rational 0 there. You don't have to set it equal to 0 or anything, because it is the 0. And I'm listing my coefficients, and there's no missing terms. And I'm going to do synthetic division. Drop your 1, multiply, and put the result here. 1 times 1 is 1. Add, you get 2. 1 times 2 is 2. And you add, you get negative 2. This is negative 2. Doesn't work, because we're going to get negative 6 for a remainder. So positive 1 is out. And so now we'll try negative 1, and we'll see if that works. And if it doesn't, then we have to try 2, and then negative 2, and then 4, and negative 4. So why don't you guys pause the video and try negative 1, and keep going until you find one that works. So when I tested negative 1 to see if it is a factor, it is a factor because I got a remainder of 0. So that means step 1 in factoring this polynomial, we can rewrite that as x. So if I'm dividing here by negative 1, then the factor is x minus that, so x plus 1, and then we're going to multiply by the quotient here, which is, this is my constant, this is my x term, the coefficient of my x term, and the coefficient of my x squared term. So it's going to factor into x squared plus 0x, which I don't need to write, minus 4. And we're going to figure out when this equals 0. This is factored, but this here is a difference of squares, which factors further. So we can go x plus 1 and then multiply or factor this difference of squares. It factors into x, and x plus 2 minus 2. And we're going to set each factor to 0. And notice all of these have a multiplicity of 1 because the factor only shows up one time. So x plus 1 equals 0 when x is negative 1, that's a 0. And x plus 2 equals 0 when x equals negative 2. And then this third guy, x minus 2 equals 0 when x equals positive 2. Okay, so I'll graph this on a calculator, and we'll see that those are indeed our zeros, and which are going to be x-intercepts because they are real numbers. So in y1 I have the equation x cubed plus x squared minus 4x minus 4, which is what we just factored. And then if I go here and I trace, what were my zeros? I had zeros of negative 1, negative 2, and positive 2. So if I trace to negative 2, there's one of the zeros, also an x-intercept. If I trace to negative 1, there's another 0, and then the third one will be over there at 2. So those are, and they're all of multiplicity 1, so they all cross through the x-axis and don't have a bend. All right, so let's try this next one. Well, when you look at this, first thing you want to do always is there anything that is common to all of the terms, which we have, all of these numbers are divisible by 2. So I'm going to start by dividing by 2, and it's going to make my life a whole lot easier. So if I do that, I get x cubed minus, what is that, 21x plus 20 equals 0. So my p is equal to 20, the constant. Q is equal to 1 again, which actually makes this a lot easier. Maybe I need to do another example afterwards where it's not a 1. But then p over q, so factors of p are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, and then plus or minus 20. And then my factors of q are just plus or minus 1. And so just like the previous example, when I put each of these over the 1, it's just going to come back to these possibilities right here. And that is 1, 2, 3, 4, 5, 6 times 2, because you have the positive and negative. That's 12 possibilities. So sometimes because, so this is what they used to have to do back in the day before calculators. Sometimes when you have a lot of possibilities like this that you have to test in synthetic division, what I would recommend that you do is you graph the original, and then we're gonna, or we can graph the factor form. We'll graph x cubed minus 21x plus 20, and then find a 0, and then factor it from there. I'll show you what I mean. So I have, in y1 I have x cubed minus 21x plus 20, which is what we got after we divided by 2. But just to show that you'll have the same zeros, with the original, which was 2x cubed minus 42x plus 40, I'm going to graph that in y2. So the blue graph is going to be what we ended up using for synthetic division. The red graph is going to be the original. When I push graph, you can see that you do have, what were our zeros here? We had, we're looking for a 0. We are, so we have the same zeros of the red graph and the blue graph. And it looks like, I'm just kind of looking to see, it looks like 1 is probably a 0. So I'm going to try that. I'm going to trace to 1. And if my y-coordinate is 0, which it is, that means 1 is a 0 for this polynomial. So what I'm going to do is I'm going to do the synthetic division. And I won't need those other factors once I find one factor because it's a cubic and I'll get it into a quadratic. All right, so my factors here are 2, negative 42, and 40. I'm going to divide by 1 because we found out that 1 was a 0. So go ahead and do the synthetic division and come back. So it goes in evenly because our remainder here is 0. And so we know that this polynomial can be factored into x. If the 0 is 1, then the factor is x minus 1 times, this is going to be 2. This is my constant. Oh, I messed up. I forgot to put in a missing term of 0. I knew that when I divided I should get a quadratic, and I only had a linear function here, so I did this wrong. So I'm going to go back. So this is what you should get when you do the synthetic division. You get a remainder of 0 still, but my quotient is going to be 2x squared plus 2x minus 40, which is what I have right here. And notice I can factor out a 2 out of that. So if I continue factoring, I'm going to pull the 2 all the way out to the front here. And I have this x minus 1. And what's left inside here is everything divided by 2, which is x squared plus x minus 20. And notice that that is a quadratic, which is further factorable. Oops, that's a minus 1. Can't read my own writing. Factor this. It factors into x, and then we have plus 5 minus 4. So it has to multiply to negative 20, has to add to 1. Set each of those equal to 0, and you get your zeros. You get 2 will never be 0, so I don't have to worry about that. X minus 1 is 0 when x is 1. X plus 5 is 0 when x equals negative 5. And x minus 4 is 0 when x is equal to 4. And so looking at my graph, I have, can't remember, 1, negative 5, and 4. So I'm going to trace to 1. You can see that's one of the zeros. Negative 5, another 0. And then 4 is the third 0 there. All multiplicity of 1, so they cross right through the x-axis and no bend. All right, well that is it for lesson 3.5. Do the practice and bring me your questions.